So how exactly does one make a color magnitude diagram using the IRSA system? I have the lab that I want everyone to do here open. There's a link to the IPAC IRSA page right to the Finder chart, which is what you need. And there are 4 examples right here. I'm going to go ahead and do PAL 3 as an example of how to do it, but all the instructions are here with screenshots, step by step, and I just want to step you through it. And then at the end, of course, there's a set of analysis questions, and I'll tell you what to turn in. So how do we use the IPAC IRSA Finder chart? So I opened it up from that link, and I'm going to search for PAL 3. So this stands for Palomar 3 and Palomar 5 and Messier 13, and the last one, the full name is there, Malat 71. So the Palomar Observatory had quite a lot of glass plates of star clusters and nebulas and things like that. And not too long ago, someone digitized those plates, and that data has been added to the IRSA database, even though we're going to be using data taken by a different survey called SDSS. So PAL3 is the name. I keep switching back and forth there. PAL3. And the size of the SDSS field to return stars for is 0.7 arc minutes. So I'm going to pull this down and choose arc minutes, and I'm going to choose 0.7. I'm actually going to go ahead with 1. That's close enough. You don't have to be exact. I can probably put 1 in there. And that's actually all the information I need. I do not want DSS. I do not want 2MASS. I don't want WISE, Spitzer, or Akari. By the way, there are sources from these other surveys that you can use, including DSS, which is the digitized sky survey, the one that actually originally took the Palomar images and turned them into data. But the SDSS robotic mission scanning the skies for stars and galaxies and quasars and unfound asteroids and other things like that. It has a lot of very useful data. So I've got the size, I've got the name, I've got SDSS selected. It doesn't really matter about the display size since I'm not really using the images. So I'm going to leave that alone. I'm going to check the box or the radio button that says search within image boundary. And let me just open the option here. So we're going to use all the filters: ultraviolet, green, red, near infrared, and even farther infrared. So we're going to go ahead and let it return all of them because it's just easier. Notice this is data release 7 right here. So I'm going to hit search. And it brings back the image, and down in that little box right there, those are all of the stars that SDSS thinks, the SDSS program, the astronomers that processed all the data. Those are all of the stars that are in that area. Not all of which are part of the globular cluster that has been going in and out of the disk of the Milky Way for billions of years. So some of them are field stars. Some of them are part of the original cluster and some aren't. So, well, I talked through what I just did there, so let me say it again. So it returns the images and it returns the data in a big table, which you can save to Excel and other things like that. This is a computational thinking exercise in an astronomical context. So this service, IRSA, part of IPAC, they have an unbelievably large amount of data, but they've created this web page as a software product for processing the data. And that's what we're doing. So we're not writing any code, but this is still thinking about data, organizing it, visualizing it. That is computational thinking. So in its own way, we're doing just that. So I'm going to hit this little button where the graph is, which is currently declination by right ascension. So this is a map of where the stars are in the sky. That's not helpful to get a color magnitude diagram, which is a weird sort of flavor of a HR diagram. So I'm going to hit the options and tools. And so the plot style should be points, not connected, not lines, but points. So a scatter plot. And along the x-axis, we're going to do the color index. So the shorter wavelength minus the longer wavelength. Remembering these are magnitudes. So if I type PSF, it brings up a list of all of the fields in the SDSS database that match PSF. So there's the magnitude in ultraviolet, there's the magnitude in green and red and near infrared and far infrared. I think I might have said them backwards before. I don't even know. So these magnitudes have already been calculated. So if I say green in there and then subtract from it PSF magnitude red. Remember, these are magnitudes. A more negative number would mean more of that type of light. So if the green minus the red turns out to be a negative number, there's more of the shorter wavelengths. If green minus red turns out to be a positive number, then there, sorry, y'all, there are more of the shorter wavelengths. I nearly choked on my own coffee. So that's what the color index is. It's an analog for temperature. More negative would be closer to the origin, just like the HR diagram has a blue closer to the origin. And then for the y-axis, we're going to go ahead and put the red magnitude. Remembering, though, that we have to go to layout options for the y-axis and reverse it because magnitude is backwards. So the backwardsness of the magnitudes actually worked in our favor on the x-axis because the HR diagram has the hotter, the bluer, the more negative on the left. So that's already right, but the way we want it. But for the y-axis, we need to reverse the red magnitude so that the ones that are more negative are closer to the top. Let's go ahead and put mag and mag for our labels. And actually, I'm just going to hit apply and close. Some of these stars are not part of this. It's a globular cluster, not an open cluster, but many of them are. So I would say that this little area right here, only this little bit, this is actually what's left of the main sequence stars in this cluster. This whole thing is the red giant branch. Somewhere in here would be the subgiant branch, and arguably at least a couple of these are probably white dwarf stars from the cluster. Again, though, we're not guaranteed that all the stars that it returned, each one of these dots is a star that the SDSS found. We're not guaranteed that the stars that were returned are part of the cluster, but that's okay. So what I'm asking you to do is for all four of them, make a color magnitude diagram and tell me where the white dwarf stars, where the red giants, where's the main sequence, which one based on the turnoff. Remember, the farther up the turnoff is, the younger the cluster must be. Two of them are globular. Wait, hang on. Yeah, no, three of them are globular clusters and one is an open cluster. So hopefully you'll find that the three globular clusters not only are older than the open cluster, but you can even tell when you're done with this, at least I believe you can, which one is the oldest, which one is the youngest from the three, which is still probably like 5 billion years old, and which one's in the middle. And theoretically, you better find that the Malott cluster is the youngest, but you know what? Maybe I'm wrong. So be careful when you're processing your data. I tell you how to do the CMD. I give you kind of example what it looks like and what to put into the fields, and I tell you what I want answered and what I want you to turn in. So you and your group work on this together, save one document that if there are three people in a group, then all three of you will save a copy of the one document you made to answer all your questions. I would even make a copy of this Google Doc and save that into your own drive, your own Google Drive, so you can work from there. And it's probably good to get on Teams and somebody share their screen so you can, do this together as a group instead of having to do it on your own. Hopefully that will get you going and you can answer all the questions and we can do this computational thinking astronomy lab remotely. All right, good luck.